Hey guys, Mr. Schultz here. I'm just popping in to go over the Chapter 7 review. Y'all didn't seem to have many questions on Friday, and frankly, I wasn't feeling myself because, well, that's another story. But, anyways, I just wanted to pop in right quick to go over the Chapter 7 review. That way you can watch the video, and if you have questions, you can pause it, rewatch it, etc. So I'm going to go over the whole review. One person asked for question 1, but I'm just going to do the whole review. So let me share my screen and we'll get started. Okay, so again, this is the Chapter 7 AP review. Dual credit, your review is posted in Blackboard, but this is the Chapter 7 AP review. So number 1, they give us this information about mating eagles. And they say that the eagle pairs typically have 2 baby eagles, which we'll call eaglets. When there are 2 eaglets, the parents always feed the older eaglet until it has had its fill, and then they feed the younger eaglet. This results in an unequal chance of survival for the 2 eaglets. Suppose that the older eaglet has a 50% chance of survival. So as I read, I'm going to make note of what's going on here. So the probability that the older eaglet survives is 50%. If the older eaglet survives, the younger eaglet has a 10% chance of survival. So the probability of young, given that old survived, is a 10% chance. If the older eaglet does not survive, the younger eaglet has a 30% chance of survival. So probability the young survives given the old does not is 30%. Let X be the number of eaglets that survive. Which of the following is the probability distribution of X? Okay, so notice I don't have X's here. I'm using O for old, Y for young, and so on. Now, what we're going to do to help us solve this is to create a conditional probability table. So I'm going to have old and old complement on top. So old survives, O complement means old dies. Then young complement, so young dies. And then of course our totals out here. And down here. So here's the table that we're going to use. Okay, so the probability that the old survives is 0.5. Which means the probability it dies is also 0.5 because we need a total of 1. Now, young given old. So old survived, the probability that the young survives is 0.1. So that's going to be a 10th of the 0.5. Remember, conditional probability, we do the intersection over the total. So 0.05 divided by 0.5 gives you the 0.1. That means, so the young and old surviving have a 5% chance of both surviving. Old surviving and young dying, well, this column has to add to 0.5, so that means I have a 0.45 chance of old surviving and young dying. Okay, so I've used this piece of information from my table. I've used this piece. Now this last piece. The probability that the young survives given the old does not, so young survives, old does not, is 0.3. That's going to be 0.15, which leaves us with a 0.35 here. Remember, like I said, this is conditional probability, so I'm going to eventually need 0.15 divided by 0.5 to give me 0.3. I've used that piece of info. So if I wanted to complete my table for this problem, you didn't have to, but we've done it this far, why not finish it? The probability the young survives period would be 0.2. Probability he dies is 0.8. Okay, they don't ask us for this table. They say, let me scroll down some. They say X equals the number of surviving. So I need to go through here and figure out, okay, how many survive? Well, X equals 0 means none survive. So when does that happen? At Y complement intersect O complement, which is a 0.35 chance. X equals 1 is a probability that 1 survives. So either Y complement and O or Y and O complement. That's going to be these two right here. So I'd have to do 0.15 plus 0.45, which gives me 0.6. And then the probability that they both survive is where young and old survive, which is 0.05. So now I need to look at my answer choices. When X is 0, my probability needs to be 0.35. When X is 1, probability needs to be 0.6. X equals 2, probability needs to be 0.05. The table that has that as its option is C. So C is our answer on number 1. Okay, number 2. A popular computer card game keeps track of the number of games played and the number of games won on that computer. The cards are shuffled before each game. So the outcome of the game is independent from one game to the next and is based on the skill level of the player. Let X represent the number of games that have been won out of 100. Under which of the following conditions would X be a binomial random variable? So we've got to go through here and make sure that our answer choices answer the properties for a binomial. So A says that all games were played by the same player whose skill improved over the course of the games. If your skill improves, does that change your probability? Yes. So this means the probability is not constant. So we can throw A out. B, a group of 5 players of different skill levels were each allowed to play 20 games in a row. Okay, if they had different skill levels, are their probabilities constant? No. So again, probability not constant. Throw it out. C, a group of players of different skill levels were each allowed to play until they had lost 3 games. And this resulted in 100 games played. They played until they lost 3 games. What's that almost sound like? Geometric. Throw it out. 2 players of equal skill level each played 1 game a day for 50 days. Their skill level did not change from day to day. All they had their equal skill. Their skill did not change. Maybe. E, 2 players of different skill level competed by allowing one player to continue until a game was lost. Then the other player continued until a game was lost, and so on until 100 games were played. This smells of a geometric distribution. So it's gone. The only one that stood the test is D. Okay, number 3. A blind taste test will be conducted with non-volunteers to determine whether people can taste the difference between bottled water and tap water. Each participant will taste the water from 2 different glasses and then identify which glass he or she thinks contains the tap water. Assuming that people cannot taste the difference between bottled water and tap water, what is the probability that at least 8 of the non-participants will correctly identify the tap water? So here, notice that we're assuming people cannot taste the difference. That means our probability of success is 0.5. They want at least 8 of the 9. Well, that means we need 8 or 9. And how many trials do we have? We have 9 volunteers, so n equals 9. So probability that x is greater than or equal to 8 is equal to the probability that x equals 8. Oh, I guess I should say here this is a binomial. Plus the probability that x equals 9. Okay, so we're going to have 9 choose 8 times 0.5 to the 8 times 0.5 to the 1 plus 9 choose 9 times 0.5 to the 9 times 0.5 to the 0. Now, if we put all of this in our calculator, let's see what we should get. So 4 decimal places, I get 0.0195. So at least 8 That means the answer is B. Okay. Let's keep going. Number 4. Hang on, my ink moved on me. Okay, now we're back in action. Number 4, a candy company produces individually wrapped candies. The quality control manager for the company believes that the weight of the candies is approximately normally distributed with a mean of 720 milligrams. If the manager's belief is correct, which of the following intervals of weights will contain the largest proportion of the candies in the distribution of weights? So let's draw an approximate normal distribution. And I'll say approximate because, yeah, I'm not an artist. So we're going to draw just an approximate normal curve. Okay, our mean is going to be right here in the middle, 720 milligrams. Okay, now, which of the intervals will contain the largest proportion? Remember, the largest proportion will always, pretty much always include the mean. So will include mean, because that's where we're the highest at. If it doesn't include the mean, it's not going to be the largest proportion. So if we look here, 740 to 780, no mean. So we can throw it out. 700 to 740, our mean is in there, so we're okay for now. 680 to 720, our mean is technically still included, so let's keep it for now. 660 to 700, no mean. 620 to 660, no mean. So now we've got a 50-50 shot. Now let's think about this. 680, I don't know what the standard deviation is, but if I'm just willing to guess, I mean, 680 would be, let's just say right here. Let's say that's 680. So that means that distance is C. Now we're going to say 700, so split it here, to 740. Notice that these contain higher points. They both contain 700 to 720, but you have to ask yourself, which is more? This area or this area? This area is higher, so it's going to be more, which means the one that's centered at the mean is going to be our biggest. Okay, so those were our multiple choice questions. Now let's look at the free response. So let's see what the problem tells us. It says inspecting meat is a very important part of ensuring healthy food. So that meat inspectors do not fall into a pattern of inspection, they use a four-sided die to decide whether or not to sample the meat from a particular side of beef. The meat inspector rolls the die, and if it comes up a 4, a sample's taken. 40 sides of beef are possible for inspection. So let X be the random variable of the number of sides selected out of 40. Okay, let's see. N is going to be 40. Now, what's the probability that he samples the meat? Well, he's using a four-sided die, and if it rolls a 4, he takes a sample. So the probability of a sample would have to be 0.25. This is a binomial distribution. Every trial, there's a fixed number of trials, 40. They all have the same probability, 0.25. They're all independent because he's not changing the die, it's the same die each time. This fits a binomial distribution. So to find the mean of X for a binomial, remember that's N times P. So 40 times 0.25, which means the mu of X, the mean of X is 10 sides. So on average, out of the 40, he'll sample 10 sides. Okay, part B asks for the standard deviation. Again, this is a binomial, so our formula for standard deviation is N times P times 1 minus P, which remember 1 minus P can also be called Q. So that's going to be sigma X equals the square root of 40 times 0.25 times 0.75. So if I calculate this, that means we want to take the square root of 7.5. So to 4 decimal places, sigma equals 2.7386 sides. Okay, number 6. They want us to use our normal table. So here they ask us the probability that Z is less than negative 2.45. You're literally just looking at your normal table. That's all you're doing. You search for negative 2.4 in the table on the side, and then at the top look for 0.05. If you look there, you'll find that that's 0.0071. That's all there is to it. Just you get it straight from your table. There's no work to be shown. Okay, next one. Probability that Z is less than 1.67. I'm not worried about that positive sign. As long as it's not negative, I'm okay. So you don't have to worry about writing the positive 1.67. Now, if it's negative, that's different. But positive, I don't know why they put it. Anyways. So again, we're just reading straight off the table. So that's going to be 0.9525. Okay, for C, the probability that Z is between negative 1.43 and positive 1.43. Remember, we have to subtract. We have to first do the big one, the positive one, or just not even the, I shouldn't even say that, just the bigger one comes first, minus the probability of the smaller one. So if I pull these values straight from my normal table, I get 0.9236 minus 0.0764, which altogether gives me 0.8472. Okay, D, what value of Z separates the smaller 10%? So I'm going to draw me a little diagram here. Yeah, that's a horrible normal curve, but still not the greatest, but we'll go with it. The smaller 10%. So we want this to be 0.9 up here, this to be 0.10 down here from the larger 90%. What is this Z right here? That's what we're wanting to find. What Z gives us this area? Putting that into our symbols, that's a probability that Z is less than Z star. And that's going to equal 0.1. So in our table, we need to look for 0.1 in the middle of the table, where all the numbers are. Not on the edges, in the middle. Find our closest probability to 0.1 and then trace it outwards. And we'll find that Z star is approximately equal to negative 1.28. Nope. Hang on, guys. My ink wants to move, and I don't want it to move. Okay, last one. What values of negative Z and positive Z separate the middle 95% of the standard normal from the extreme 5%. The middle 95%. So if I draw a standard normal curve, I want the middle here to be 95%. Which means I want my outside values here to be, remember, we're symmetric, so we have to split it in half. So this will be 2.5% in that area. That one's going to be 2.5%. What are these z's? And they're symmetric. So once you find one, just throw a negative on it and you get the other. So I'm going to find the one, since it'll be the easiest for me to do. I'm going to find P, that z is less than z star, is equal to 0.0250. Let's find that one. So when we do that, we'll see that negative z would be equal to negative 1.96, which means positive z is equal to positive 1.96. So these are our two values right here. Again, this is like doing that reverse lookup. At least that's what I call it. Got to find the z that gives us this probability. So there's number 6. Number 7. So while playing Monopoly, Laura estimated the probabilities of non-zero rents according to the probability distribution. Consider the random variable x equals dollar amount in rent in a Monopoly roll. So first they ask us to find the mean. Well, since this is just a distribution, the mean is the sum of your x times your probability. X times the probability of x. So 10 times 0.2 plus 20 times 0.2 plus 50 times 0.4 plus 130 times 0.2. If we add all of those together, we'll find that our mean is equal to $52. Okay, now part B asks us to find the standard deviation. So they ask us for standard deviation, but to get that, we've got to first get the variance. So variance, remember, that's the sum of the squared deviations from our mean times the probability that they occur. So this is going to be a longer one. We have to do 10 minus 52 squared times 0.2 plus 20 minus 52 squared times 0.2 plus 50 minus 52 squared times 0.4. And last but not least, 130 minus 52 squared times 0.2. Add all these up, and we'll get 1776 as our variance. It doesn't ask for variance, though. It asks for standard deviation, so we've got to take the square root of it. And to 2 decimal places, we're dealing with money here. So 2 decimal places, we'll get $42.14. So there's our mean, there's our standard deviation. Okay, number 8. In a major study about a statistics class at Jefferson High, parking spaces were examined for compliance with the requirements to put money in the meters. Overall, students found that 80% of metered parking places had meters that had not expired, and 20% had expired. If the traffic officer in charge of ticketing cars with expired meters and he starts at a random location in the city, what's the probability that he or she will find an expired meter before the third one? We want to find an expired meter. So what that means is that X equals the number of expired, hang on. The number of meters until an expired. So that means this is a geometric distribution. So the probability that X is less than 3 is what they want us to find, which is the probability that X equals 1 plus the probability that X equals 2. Well, what is the probability of a success? So P is equal to, well, it says 20% expired, so 0.2. Well, probability that X is equal to 1 is just 0.2. Plus probability X equals 2. Well, we had 1 failure, and then we had a success. So that means our probability would be 0.36. There's our answer. Okay, number 9. In a study of the reaction times of left and right-handers' reaction times to tones delivered to the right ear, the left-hander scores were approximately normally distributed with a mean of 240 milliseconds and a standard deviation of 32 milliseconds. So mean of left 240. Standard deviation of left is 32. The mean for the right is 210. Sketch a normal distribution that describes left-handers' reaction times and locate the mean reaction time for the right-handers. So again, we've got to draw a standard normal. I'm going to say right here, well, right here is my mean for left-handers. Then we go one standard deviation out, 2 out, and then 3 out. So this, I'm going to rewrite this for a second. So UL is right there. There's 240. Each one of these tick marks is a standard deviation. So this is 208. This one is 272. Okay, now it says that right-handers have a mean of 210. So we're going to be just before this 208. And I'm going to make a note here. That's the mean of the right-handers at 208. So that's what it's asking us to do. Now, what proportion of left-handers' reaction times would be better than the mean of the right-handers? Which, remember, better means smaller here. So we want this area right here. What's this area equal to? Okay, well, that means we want the probability that L is less than 208. We've got, sorry, not 208. I just caught that. This is not wanting to select. That should be 210, not 208. Okay, well, to do this, we need to standardize the probability that Z is less than 210 minus 240 over 32. Which means we want the probability that Z is less than to 2 decimal places, since that's all our table gives us, is negative 0.94. Which equals 0.1736. So that's the proportion, 0.1736, that would be smaller. Okay, last one. In a certain very large city, the Department of Transportation has organized a complex system of bus transportation. In an advertising campaign, citizens are encouraged to use the Go DOT system and head for the nearest bus stop to be transported to and from the central city. Suppose that at one of the bus stops, the amount of time in minutes that a commuter must wait for a bus is a uniformly distributed random variable. That's important here, uniformly distributed random variable. The values of t run from 0 to 30 minutes. Uniformly distributed means all values have the same probability. So they want us to sketch the probability distribution of t. So I'm going to draw my axes here. 5, 10, 15, 20, 25, 30. And then my y-axis is my probability, so 0.01, 2, 3, 4, 5. So this is minutes. This is probability of x. Okay, now they all have the same probability. And remember that the area under the curve has to equal 1. So there's 30 minutes. That means the probability of any given x is just a straight line at 1/30th. So 1/30th is our probability here. It's going to be a constant 1/30th. Which is approximately equal to it's like 0.033333 repeating. So just slightly above the 0.3 right here. So that's what it looks like. It's just a straight line all the way out to 30. This is 1/30th right here. So that's all we have to do for the probability distribution, is just draw the graph. B asks us, what's the probability that a random commuter will spend more than 12 minutes waiting for Go DOT? So I'm going to come up here to the graph I just drew to figure out what region I need. So 12 is, I'd say about right there. So more than 12 means we're wanting this area in here. What is this area? Well, how far up did I go? I went up 1/30th. This is just a rectangle. I went up 1/30th. How long am I? from 12 to 30, that's 18. So the probability that t is greater than 12 equals 1/30 times 18, which is 0.6. That's what we're wanting to find. Okay, so there's the review. The key is uploaded. Now y'all will have the video to go with it. So hopefully you study this weekend. If you have questions, you know how to reach me. See you Monday.